Okay, today we're going to talk about groundwater. One of the things to keep in mind is how important groundwater is to us, not only as a species, but as a civilization. Basically speaking, when you look at the distribution of water on the planet, roughly 96.5% of all the water on the earth is found in the oceans. That's salt water, very high salinity salt water, at least in terms of what we can consume. You consume a cup of salt water, that potentially could kill you. Um, of all the water on the earth, only about 2.5% is considered fresh water. Of that, only about 30% of it is groundwater. The vast majority of it, roughly 69% or so, is actually water that is frozen in the form of glaciers or ice caps or permafrost. So the ability to access water is one need that we have, and it turns out that groundwater is the largest resource for that. So in areas, especially like in the American Southwest, groundwater is the major source of water for the majority of people. Now, it does have several geologic roles we can talk about. It does act as an erosional agent. We will see that groundwater, in interacting with limestone, can actually dissolve limestone, forming caves or sinkholes and caverns. It also will equalize stream flow in certain environments. So you can have streams that gain water from the groundwater system, or they lose water to the groundwater system. So let's look at where we find groundwater to begin with. So we're going to start with a bit of a profile similar to a soil profile. I'm going to start with the surface, and we're going to put down here something we're going to refer to as an aquitard. Okay, and all an aquitard is a rock layer that will not allow water to move through it. It's a rock layer that's impermeable and non-porous, basically. So water cannot move through it. Now, let's start this by thinking about rainfall. We talked about running water last time. We had rainfall. We'll start with rainfall again. Rainfall. Now, instead of following the path of water through the runoff, we're going to follow it through infiltration. So we have the water going through into infiltration. This is going to create, near the surface, a belt of what we call soil moisture, or the soil moisture belt. This is basically, that's going to be water that's going to be held in molecular adhesion or molecular attraction to the particles of soil. Some degree of this will not be able to be used. It's bonded so tightly it cannot be taken off by plants. The rest of it can be used by plants. Now, there is a maximum amount of moisture that can be held in this belt. It is going to be controlled in part by factors such as the type of minerals that are present in the soil, the size of the particle grains, but also the amount of soil carbon or organic material that's available. Recent studies have shown a very interesting fact, if they hold up in follow-up studies, and that is every 1% of organic material you add to a soil within the upper surface of the soil can increase the holding capacity of the soil moisture belt by about 1 acre-foot per acre. What that means is that if you take an area of land 1 acre in size, or 43,560 square feet, and add 1% more carbon to that soil, say within the first foot or two of the surface, that ground can then hold up to 1 acre-foot of water more. An acre-foot of water is roughly 1 foot of water over the surface of an acre, or 43,560 cubic feet of water. Now, this is preliminary studies. It needs to be verified, but it's an interesting thing. It actually looks at ways that we can try to increase the amount of infiltration and water that we get into the land and help reduce runoff to mitigate basically the effects that urbanization and construction have on increasing runoff and increasing the amount of flooding that we can potentially have. Now, below this, we will have a layer of some sort, below which the pores of the ground all are completely filled with water, and this is going to be the zone of saturation. So no matter where you look in this, if there's an open space that's interconnected, it will be full of water. Okay? The top of this is what we call the water table. So if you were to dig a well through this, I'll do it on this side over here, so I don't have to erase too much. The water table would basically be what the top of the water in the well would be, okay? Essentially, for all intents and purposes. Now, it doesn't mean that's the only spot you're going to see water, because above the water table, if I can spell, is something called the capillary fringe. The capillary fringe is a product of the nature of the water molecule. We've mentioned it before that water is a dipolar molecule. I believe I've mentioned this before, at least. I know I have in other classes. I just can't remember now for this one. What that means is that when you look at the water molecule, you have the oxygen and then you have the two hydrogens coming off of it. The two hydrogens tend to have an angle of 120 degrees between them. This creates a molecule in which one side of the molecule has a positive charge, the other side of the molecule has a negative charge. Hence the reason we call it dipolar. This means that water is going to try to line up electrically. It's going to have an electrical field and it wants to line up. It wants things to be neutralized. This creates the surface tension of water. If you've ever floated something like a paper clip on water or seen a bead of water on top of water, it's caused by the surface tension. Or like we can kind of see in my T here, you can kind of make up at the edges where the water kind of curls up the side of the cup. That is a function of the surface tension that we call capillary action. The water wants to climb up those surfaces. Now, interestingly enough, the smaller the diameter of the opening, the higher the capillary action will carry the water. So you can test this by getting different straws if you can find clear ones. Really skinny straw that's clear and a thick straw, a fat straw that's clear, and you can put them in to the water, and you can see that in the smaller straw the water will rise significantly higher than in the thicker straw. So again, we can actually use this to help us understand what's happening in the ground here. Based on the particle size of the materials, the water is lifting itself upwards through capillary action. The way we would see this in our well is we would see drops of water coming out of the side of the well in the area of the capillary fringe. Now, since not all the water is held by the soil moisture, it's going to percolate down and it's going to fill in those spaces. So the elevation of the water table is subject to fluctuation. It can change. It can move up in wet years and down in dry years. The area above the water table we typically call the zone of aeration. This is basically going to include both the soil moisture belt and the capillary fringe, but basically it's an area where you cannot pump water from. Now, interestingly enough, besides the seasonality of water tables, they can also behave based on the topography. This is because the water table behaves to a degree related to pressure. So the water table surface in an ideal situation, will be a pressure surface. It's going to be a surface of equal pressure. So it will move up and down with topography in order to reach those pressures. So the surface of the water table will, to a degree, mimic, although it will be subdued, i.e., it will not be as pronounced, the topography above it. So in areas that are higher, the water will be a little bit higher under them. Areas that are lower, the water will be a little bit lower under them. We also can have variability based on the nature of the rocks or the material that it's trying to move in. We'll talk about that in just a little bit. But I want to touch on a couple of other things that can have an effect. One in particular. So to show this, I'm going to draw a hypothetical situation of two neighbors. Well, hypothetical but real. All right. You have two neighbors near each other with wells. Okay, this is going to be neighbor one. That's the person that's been there the longest. This is neighbor two, the person that came in. Now, when you have a well, what typically will happen is you're going to remove groundwater from the water table, from the zone of saturation, slightly faster than the water can recharge that area. This is going to create what we refer to as a cone of depression, like that. So the water table will be depressed in that area, and that's an effect of the pumping of the well. So that's the cone of depression. Turn the well off, that will rebound, ultimately. But what if I got two wells next to each other? Well, this other well goes a lot deeper because they're pumping a lot more water. It can have a much bigger cone of depression. The more water you're pumping, the bigger the cone of depression. What happened to this well? It went dry. Actually, the situation did actually happen like this in the Casa Grande area. One of the pecan growers had a well that went dry because a plastics manufacturing plant went in next door. And of course, plastic manufacturing is much more water intensive than the pecan groves were. And it sucked the pecan groves dry. Weirdly, under Arizona state law, somehow which treats water as a mineral right, i.e., if you own the land and you own the mineral rights below it, I gotta stop the puppy from licking the whiteboard. You own the water. The Arizona Supreme Court, in some way, decided in a case that the plastics manufacturer, who was newer, didn't own the water rights under the pecan farms, had right to that water because they had more jobs and a greater impact on the economy than the pecan groves. It's a bizarre case, what can I say? But it's one that's there. But it gives you an idea of how, when we are planning out our water systems, we have to have an idea about the impact that our pumping on those wells is going to have. And that's something that the Arizona State Department of Water Resources actually does look into. Now, we'll talk about some more of the effects of groundwater pumping in a little bit. There are some effects that can be rather disastrous that we will look at. But I want to move on to talking about this interaction with streams. Basically, we can have three interactions with streams in the groundwater system. You can have what's called a gaining stream. This is where water is pouring into the stream from the groundwater table. This can be very effective in keeping a stream running, especially during drought periods or in certain areas that are more arid conditions. For example, if you go down by Tubac, Arizona, along the Santa Cruz River, there are some spots there where you can find the sand in the river bottom looking like it's boiling, it's bubbling up. This is where groundwater is entering the riverbed. Of course, we can have the reverse of that, which is a losing stream, where the water from the stream is soaking into the ground. Very common thing to see in the desert Southwest, especially during the monsoons. We have a rainstorm. We have a stream that starts flowing, a wash that starts flowing, and you can go to the end of that flow, and you can see where that water is just kind of soaking into the ground. And the stream is basically stopping at that point because it's soaking into the ground and becoming part of the groundwater system. And then, of course, nature wouldn't be nature if you didn't have any combination of the two and some degree of variation between the two, from 100% to 0% on one end to 0% to 100% on the other end. Now, what are the factors that influence the storage and replacement of groundwater as well as its movement? Well, primarily speaking, there are only two factors that we have to be concerned about. The first of these is porosity. Now, porosity is most easily defined as the total volume of open space or pore space within a material. So if you think about a typical building, you think about the volume of a typical building, most of that building is open space. So it would be considered very porous. It has a lot of open space to it, 90+%. If you think about a pile of silt grains and a pile of cobbles, or gravel, which one's going to have more porosity? Well, the larger the grains are, the larger the porosity will tend to be, the more porosity you will have. Silt grains are very small, less than 1/16 of a millimeter, down to 1/256 of a millimeter. So they're not going to have a lot of porosity in them. But gravel, which is anything larger than 2 millimeters, can have a lot of porosity in it. So this basically is going to determine how much groundwater can be stored within the material, or how much water can be stored based on that volume. Permeability, on the other hand, is basically defined as the ability of the fluid to move. I like to think of it as the interconnectivity of the pore spaces, of the openings within. Think of it this way. Let's take a trip back in time. Let's go to high school. I'm sure everybody can picture in their mind a teacher in high school they absolutely, positively did not like. Everybody seems to have had one, so we'll use this as an example. I want you to now picture you're in that classroom. No doors, no windows, no way to get out of that building. And you got to get to your next class. How do you do it? You can't. Okay, unless you dig through something or whatnot. We're not going into altering the building. You have to do everything as is. You can't. You have to slowly find a way to phase through the wall. Now, if we put a door in every wall, it's easy to move in and out. Well, that's pretty much what permeability is. Permeability is how do we interconnect those spaces so that the water can move from one location to another. So an aquitard, as we used the term before, is a layer that's impermeable. The water cannot move through it. An aquifer, on the other hand, is going to be a material that transmits groundwater freely. A good way to think about it is that you can have something that is very porous but impermeable. You can have something that is rather permeable but non-porous. So it works both ways. The combination of the two, of high porosity and high permeability, makes great aquifers worldwide. So best aquifers we tend to find are going to be sand and gravel layers. Now, how does groundwater move? Well, one, it can move pretty slowly depending on the nature of the system, the porosity and the permeability. Some areas, water can move as little as a couple of centimeters or less a day. In other areas, it can be measured in feet per day. But that's about it. It's not going to move as fast as running water on the surface, which can move miles in a day. Its energy is going to be provided basically by gravity and, again, also pressure. So one of the reasons why water will flow in this example is you have a suction force here, and it's going to pull the water towards the well. Okay, so that's going to also be pressure. Systems will flow by both gravity and pressure. It's going to depend on which one is going to end up being the stronger force at that time. We can also look at what's called Darcy's law and work out hydrologic gradient, the head, which is the difference between the vertical elevations in different locations. I'm not going to test you guys on that. It's getting into hydraulics, and it's a little bit into the weeds, I think, for the purposes of this class. Although one of the ways we can measure groundwater is we can use what's called an injection well and inject materials into it, such as dyes or carbon-14, and then look for it to come out in the well or the spring or whatever later on. Now, one thing I will say about groundwater is we can actually age date groundwater. Now, this is an interesting little tidbit. We can do this because we can look at the ratios of oxygen 18 to oxygen 16. The interesting thing about that is that gives us an idea about how we should consider the groundwater. Groundwater resources that recharge fairly quickly, i.e. have a young age, can be treated as a renewable resource in my mind, because they will renew in a short period of time. Groundwater systems that have an old age should not be treated as a renewable. They should be treated as a finite resource. So, for example, if you go get a glass of water in Tucson prior to the use of the Colorado CAP, Colorado-Arizona project, which brings water from the Colorado River throughout Arizona. Closest one to us in Santa Cruz County is going to be Tucson, somewhere near Green Valley, I think it is. But they're using the water from the Colorado to make up for deficiencies with the groundwater system and not have to use the groundwater. One of the oxygen isotope studies for the Tucson area shows that the groundwater in Tucson is between 12 and 14,000 years old. It's the last time I had contact with the atmosphere. That indicates that that aquifer is not recharging. Let me say that again. That indicates that aquifer is not recharging. It indicates that if it is recharging, it takes a very long time to recharge. So we should treat that groundwater as a finite resource, one that is not going to replenish itself anytime soon. So we should look at that sort of a study for other areas to kind of give us an idea of what things we need to do in order to better prepare for droughts and whatnot. So what are some of the features associated with groundwater? Well, there are springs, which is basically any point where the water table intersects the surface of the earth. They can be permanent, they can be temporary, but it's a natural outflow of water. It can be caused by an aquitard, a localized aquitard that is forcing the water to the surface as well. A version of a spring is called a hot spring. Now, a hot spring has a very interesting definition to it. It's kind of a weird one. It's not a specific temperature of water that makes a spring a hot spring, but it's the average temperature of the water in relationship to the mean annual air temperature of the locality. So if the water temperature is between a minimum of 6 to 9 degrees centigrade hotter than the average air temperature of the locality, then that is going to be a hot spring. So if you are in an area where the average air temperature is, say, 45 degrees Fahrenheit, then water coming out of the ground that is on the order of 68 degrees Fahrenheit is going to be considered a hot spring. Now, you want to get into it? Probably not. Most of you will think it would feel cold. I can tell you from personal experience that 68 degree water at 4:30 in the morning will wake you up. When I was in high school, I was a swimmer, and our pool was outside for practice in Sierra Vista. for the first half of the season, and by the time late October got there, that water was not warm at 4 in the morning. Another feature that we can have are geysers. Now, geysers are an interesting feature from a geologic standpoint. We can consider them to be intermittent springs, intermittent hot springs to be exact. And the reason for this is the water doesn't come up to the surface all the time, it comes up intermittently. It comes up at different periods of time, but it comes up with great force usually. And we tend to see geysers in association with igneous rocks, especially hot igneous rocks, typically active or recently active volcanic areas. Basically, what happens is you have a complex chamber underneath, something that could look like this. Maybe it's some sort of a complex labyrinth-like system of small chambers that are all interconnected like that, just to draw something up. It fills up with water. Let's say the groundwater table is about here. So all of that area fills up with water, and that water begins to get hot. Now, one of the things you might be aware of is that the temperature at which water boils is dependent on pressure. The higher the pressure the water is under, the higher the temperature the water has to reach in order to reach its boiling point. This is why water boils easier here in Arizona than it does at sea level. We're higher up, therefore the air pressure is lower, water boils faster. Therefore, it also boils at a slightly cooler temperature. This can cause an interesting effect. Now, when things heat, they expand, so the water is going to start to push upwards. As it does, that kind of lowers the pressure in the system. Once the water reaches the surface, you can get a cascading eruption where the pressure is decreasing, and down at some depth, that water is then instantaneously turning into steam. Now, the expansion ratio from water to steam is roughly 1 cup of water becomes roughly 1,500 cups of steam. So it's a very rapid expansion, aka an explosion, if you will. And this causes the water to be erupted at even greater force once that water starts flashing into steam. Now, we do tend to get chemical sedimentary rocks associated with this because hot water can dissolve minerals. The hotter the water is, the more stuff it can dissolve. Once you get up above a certain temperature, it will dissolve quartz even. So quartz will actually dissolve in the water. So you can have what's called siliceous sinter, which is dissolved from dissolved silica, i.e. quartz, or you can have travertine, which is from calcium carbonate. And of course, we have the wells. We've kind of talked about the wells, how we can have the draw down the cone of depression around them. But a type of well we didn't talk about is called an artesian well. Artesian wells are very interesting. Now, I won't go into the legend of the Artesians, which are the cousins of the leprechauns that immigrated to North America long before the first European settlers came over and lived in the mostly in the American Southwest. One of them, named Pedro, was actually responsible for naming the San Pedro River because he was missing for a while, and they asked him where he'd been, and he took off his shoes and dumped out a bunch of sand, just said sand, so they named the area the San Pedro. Yes, it's a joke. I know it's a bad one. So an artesian well is an interesting geological situation. You have a series of layers. And at some point, there's something that pinches out the layer. Could be a normal depositional stoppage pinch. It could be a fault line. It could be any number of things. But what we end up with is something like this. Situation like sort of like this, where we have three layers. In this case, we're not going to look at what's geologically below this, but we have an aquitard on top of an aquifer layer on top of an aquitard layer. And at some point, the aquifer layer pinches out. It just, the sedimentation stopped for whatever reason, and then the sedimentation layer for the aquitard material continued on. And so a good example of this would be the aquitards would be shale, and the aquifer would be sandstone. Now, they're bent up and exposed in a mountain range where it's going to get a lot of precipitation. And let's just say, for whatever reason, we've had some sort of erosional feature where the water is going to be running down towards the aquifer material. The aquifer material probably is a little bit weaker cemented, so it wears away faster, so it becomes a depressional area. So water runs to it and gathers to it. This is going to create a situation where the water table could be, say, this line up here. Okay, we'll make that the water table. Now, you can draw from this what's called a pressure surface based on how deep the water is. And so that pressure surface might look something like this, that dotted line. Okay? If I would, an artesian well, by definition, is a well that once drilled, the water surface elevation in the well will be higher than the surface of the water in the unit of rock. So it rises up. So if I drilled a well up here, and it's going to be a little hard to see. If I draw a well up here, the water surface elevation is going to come up to here. Now the water is actually at this level down here, but it's going to rise up to here. This would be a non-flowing artesian well example. If I drilled the well lower, say down over here, the water is going to actually push up until it reaches the pressure gradient surface. So the water will shoot up until it reaches that surface roughly, and then cascade back downwards as a fountain, basically. That would be called a flowing artesian well. Now, not all artesian wells are wells. You can have artesian springs as well. But those are natural systems where the water surface is the water is coming up usually through a crack, like a fault or a joint in the rock, or a weak point in the rock, and it found its way through. Now, what about problems associated with groundwater? Well, in many areas, the aquifers are recharging much more slowly than they are being drawn down. This creates a couple of different problems. One is subsidence. It turns out that the pressure of the water in the aquifer helps to maintain the openings of the pores. When you remove the water, the weight of the overlying material compresses that down and causes what's called subsidence, the lowering of the ground level. This happens in a number of different environments all the time. It's a very common occurrence in delta deposits because those deposits are laid down in a lot of water. As the weight of the sediment squeezes out the water, the delta sinks and provides more room for more sediment on top of it. This actually explains problems with the city of New Orleans. The city of New Orleans, when it was founded, was at its highest point somewhere around 30 feet above sea level. Today, the highest point in New Orleans is only about 5 or 6 feet above sea level. It's dropped 25 feet, 24, 25 feet in about 300 years. That's a bit of a problem, especially where now most of the city of New Orleans is actually below, let me say that again, below sea level. Hence all the levees around it to try to keep it dry. I just lost the name of the valley. In one of the valleys in California, between roughly 1912 to today, the ground level has dropped by roughly somewhere between 25 and 28 meters, or 78 feet or so of drop down. 78 to 85 feet of drop where the ground has been done, has collapsed down. In parts of Arizona, we can see this also. You can see it in some parts of Tucson, where you can find cracks in the roads and sidewalks that are circular in nature. And you will find that if you find those cracks, they're not completely circular, they're more like little arcs of around the circle. But if you find those cracks, at the center of them is a pumping well every time. In other parts of Arizona, in the Phoenix area, you have subsidence cracks, which can be tens of feet deep and a foot wide from groundwater being pumped out. So the groundwater the ground sinks. San Joaquin Valley, that's what I was thinking of, in California. So the ground sinks as a result of over pumping the water. This also, especially if you're on an island environment like Hawaii, or a coastal environment like Florida, cause contamination, because you can overpump so much that you now suck salt water into the system. And of course, that contaminates the water to the point where it's undrinkable. Now, contamination also is a major problem. Common source of contamination, unfortunately, is sewage. We see that here a lot because the sewage system in Mexico leaks like a sieve. In fact, there was an incident about 10-15 years ago now, where a dog carcass got stuck in the sewer line in Mexico, and instead of trying to get the carcass out of the sewer line right away, they opened up a valve and let all of the raw sewage pour into the Nogales wash channel for a month before the dog carcass rotted to the point where it flushed itself out. So you had raw sewage running through Nogales for a month. We also have that problem with septic tanks. Septic tank systems can cause contamination, which is why a septic tank system has to be set a minimum distance away from a well to at least provide some degree of filtration. Usually it's a few dozen meters of soil material, ground material, that's needed to purify the water. We could do this. We could make up a little filtration system to show you what happens with a lot of material, where you use a clear tube, put some gravel in the bottom of it, drill a hole in the, put a cap on the bottom, drill a hole in it, put some gravel in, and then different layers of sand and material, and come to the top, pour muddy water in, and you will see that as that water percolates through, it looks clean. It looks clear and clean. That will filter out any physical particles above the size of the pores that the water is trying to go through. It doesn't get rid of chemicals. Chemical contamination is also another place that we see contamination of the groundwater, whether it's salt being used to get ice off of roads, fertilizers, pesticides, chemicals that are leaking from storage tanks, cars that are leaking fluids, holding ponds, gas stations, etc. We have a lot of regulations in place now to try to minimize that, especially with gas stations and other holding tanks, but it doesn't do anything for the old ones that are still in existence until they get upgraded. But basically, any sort of material that can disperse or be dissolved in water is a contaminant that the ground isn't going to filter out. In fact, it used to be a lot of people would take, when they change the oil in their car, they'd pour the oil on their driveway or where they would park to try to help cut down on dust. That oil works its way down into the groundwater system and contaminates it. According to the EPA, in order to contaminate 1,000 gallons of water, which is roughly a large swimming pool, it takes about 1 drop of oil, just 1 drop, to contaminate 1,000 gallons, to the point where it shouldn't be drank, according to the EPA. Now, groundwater can also do work. It will dissolve rock, in part because water tends to be slightly acidic. It's slightly acidic because of carbon dioxide. When carbon dioxide uh, dissolves into water, it turns in the water into what's called carbonic acid. It's a very weak acid, but it is an acid nonetheless. So it will dissolve carbonate rocks, especially limestone, and it will react to form calcium bicarbonate, which is basically a soluble material. Now, the interesting thing is that calcium bicarbonate, with a little bit of energy imparted into the system, that chemical reaction will reverse in the other direction, creating calcite with carbon dioxide and water. So it can go both ways. This is interesting because of what it can create, namely caves and caverns. So most caves and caverns are created by acidic groundwater that's working its way through joints or fissures or cracks of some sort in limestone, dissolving the limestone that is underwater. And that's the key, underwater. So the areas that are caves, when the voids opened up to form the cave, they were underwater. They were below the groundwater table. The features that we associate with a cave, however, are formed when the cave is above water, so in the zone of aeration. So caves form when they're under the zone of saturation. In the zone of saturation, cave features form in the zone of aeration. Now, this aeration is created by a form of travertine that we call dripstone. Basically, the gist of it is you have the rainwater, which is slightly acidic, passing through the material above the cave, dissolving limestone calcite in there, bringing it into the cave. As it drips from the surface, energy of the dripping motion and the energy of the splash at the bottom reverses the reverses the chemistry and causes the deposition of the calcite. And so it creates a dripping it can also be formed as the water evaporates, but part of it's going to be the energy reversal. All these materials, these features, are called speleothems. There's a lot of them. I got a nice sample of a stalactite that I was donated to me for teaching purposes at the college. I can't get to it; it's locked up. But hopefully at some point you guys can see it when the college opens back up, hopefully this summer, fingers crossed. You guys can look at the cabinet there and see it. It has an interesting feature on it called cave popcorn, which are these kind of popcorn-like growths on stalactites, stalagmites, and columns that are caused by evaporation specifically, and it indicates airflow within the cave. But you can have these features, stalactites and stalagmites. Now, confusion usually comes into the students on which one's which. Very simple. The spelling tells you. The word tells you if you listen to it. Stalactites has a C in it. C for ceiling. They hang from the ceiling. Another way to think of it is tight. Stalactite. It hangs tight to the ceiling. So that can help you. Stalagmites, G for ground, or mite. It might be a stalactite, but it isn't. It might be on the ceiling, but it isn't. Okay. You can also get columns, which is when a stalactite and a stalagmite grow together and meet. You can get cave shields, cave bacon, soda straws, all sorts of different features that are really cool. Wish we could go to Kartchner Caverns for a tour, but that's not going to happen right now. But this can also lead us in areas that are dominated by limestone bedrock to something called karst topography. Karst topography are landscapes that, for the large extent, maybe even the majority, were shaped by groundwater dissolving the rock rather than erosion from water moving over the surface. Some of the common features in karst topography tend to be irregular terrains, sinkholes or sinks. A sinkhole is a depression that has reached into a cavern or a cave below. A sink is just a depression above it. You can think of it as if there's a cavern down here, a sink is when the ground is just kind of bending in, and a sinkhole is when it's collapsed open. You can also have a lack of surface drainage. You can have what are called disappearing streams, streams that just kind of go into a hole and disappear, flat out disappear. Then you can also have karst towers. Now, the best explanation of karst towers I can give without being able to show you one right away is if you've been to a Chinese restaurant and they have the paintings, the landscape paintings, and you see the mountains in the painting that look kind of like this. These rounded domes, basically, vertical domes. Those are called karst towers. Those are actually remnants of a thick layer of limestone that has been dissolved away. Those are just the remnants. It indicates very large layers, very large volumes of limestone that have been dissolved. Very common in southern China. There's typically steep-sided hills. They tend to be formed in areas that are tropical to subtropical, that have very thick limestone with a lot of joints and bedding in it. So with that, that's going to finish up the discussion for water. We will be coming back and we'll talk about, I believe it's going to be glaciers next. We got glaciers, coastlines, deserts, and wind to cover, as well as a delve into planetary geology. So with that, I will let you go, and I will talk to you guys later.